In the pursuit of beating video games even faster, some lines will be crossed in the name of computer science. I'd like to emphasize that the point of this video is to go too far. In this video, I will be showcasing a new method I've been working on for executing arbitrary code on the Nintendo Entertainment System. Along with explaining how the exploit works, I will be demonstrating a use for this exploit in 4 runs. Super Mario Bros. 3 completed in 5 microseconds from pressing the reset button. Super Mario Bros. 3 completed in 17 microseconds from pressing the power button. Super Mario Bros. Completed in half a millisecond from pressing the power button, but the graphics are all messed up. And Super Mario Bros. Completed in 22 milliseconds from pressing the power button, but the graphics are clean. Well, let's not waste any time. As a bit of a warning before we get started, there will be a lot of footnotes on screen. These footnotes are entirely for people looking for more information while also not bringing the pace of the video to a halt for those who aren't. Let's begin. How do computers work? Specifically, how does the CPU of the Nintendo Entertainment System work? No, really, that's how we're starting this video. I promise this will be less intimidating than you might think. You don't need to know anything about assembly programming going into this video, but you will hopefully understand a little bit by the end. A programmer might write some piece of assembly code, and the CPU would run this code one line at a time. Logically, the CPU needs to keep track of what line to run next. Except there are no lines when you actually look at the assembly code as it exists on a cartridge. It's just bytes. How does this work? Allow me to use an analogy. Consider a board game. The board consists of about 65,500 tiles in a horizontal row. Every tile has both an index, called an address, and a value, called a value. These indexes and values are typically shown in base 16, hexadecimal. This is because an 8-bit value, or a byte, can be neatly represented as 2 digits of hexadecimal. This board will have a single player character labeled PC. It actually stands for program counter. The way this board game works is incredibly simple. The player advances to the next tile, and the value on the tile refers to an instruction. You do the instruction, then advance to the next tile. This process repeats forever or until the game crashes. Let's see an example. The player advances to the next tile, A6. Luckily, you don't need to know what that value means. That's what we have the Dungeon Master for. Alright, A6, we're gonna run a load instruction. Advance! The player advances. Get me tile 0A. Ram swoops on in. Can you write that down? Yeah. Very good! Advance! The player advances. Decrement that number. You know, subtract 1 from it. Yeah. Advance! And that's how computers work. Here's the code that was just executed in that example. Obviously, there isn't actually a dungeon master inside the CPU. For the purpose of this analogy, that's just the logic of the CPU being personified. The purpose of this analogy is to visualize how the CPU is working. The program counter points to the next byte to process, and 1 byte is processed at a time. These bytes form instructions. Just so we're clear, most programmers programming in 6502 assembly have probably never even needed to know what byte values correspond to what instructions. It is also not required information for this video, as I will be converting bytes into instructions for you. But we are going to be looking at a lot of raw bytes in this video, and it's worth knowing what's going on. For this video, I think the board game analogy has served its purpose. Let's start making some progress towards beating Mario 3 in 5 microseconds. To begin with, let's see how these bytes exist on a cartridge instead of a hypothetical board game. If we were to look at a specific address, we could see the value of the byte there. In this case, Super Mario Bros. Has the value hex A9 at address 8002. This is an LDA immediate instruction. The following byte at address 8003, hex 10, is the operand of the instruction. This instruction, LDA 10, simply sets the value of the A register to 10. Equivalent C code would be A equals 10. Let's take a look at another cartridge, for instance, Tennis. Address 8002 in this cartridge is AD, an LDA absolute instruction. The following 2 bytes are the operands, 02 and 20. Keep in mind, and this is very important information that forms the basis for this entire video, the LDA instruction does not happen in one instant. We can measure how long an instruction takes in CPU cycles. This instruction takes 4 cycles. Cycle 1 reads the opcode AD. AD denotes the LDA absolute instruction. Cycle 2 reads the first operand, 02. Cycle 3 reads the second operand, 20. With these operands combined, we form the target address for the LDA instruction, address 2002. And Cycle 4 loads the A register with the value read from address 2002. Again, it's very important you understand that each of these bytes are read at different moments in time, which gave me an idea. Hypothesis: I could swap cartridges between CPU cycles in order to execute custom code. To bring back the board game analogy, this would be like having the board get replaced with a different board every time your character takes a step. Or suppose you've invented a more optimal route through your grocery store where the entire store is instantly disassembled and reassembled in a different configuration with you still in it for every item on your shopping list. Imagine if instead of reading AD0220, I swap cartridges between cycles to read AD from tennis and 108D from Super Mario Bros. This is Intercycle Cart Swapping. That previous example, AD108D, LDA address 8D10, isn't all that useful, but I think it at least explains how this will work. Per the hypothesis, I imagine there's some set of cartridges allowing me to execute code that will take the fewest cycles to beat Mario 3. With this general explanation of how the NES CPU works, you should be able to follow along. To begin with, the 5 microsecond task. I will go into more detail when talking about the task that starts from pressing the power button, but there are a handful of conditions that need to be met in order to reach the victory screen of Super Mario Bros. 3. A lot of these conditions would have some resting state if the console was powered off, but would keep their current state through pressing the reset button. If we were on the title screen of Super Mario Bros. 3 and pressed the reset button, all we would need to do in order to see the victory screen is move the program counter to address 8FE3. If you are familiar with the 80% speedrun, you might recognize that address. Address 8FE3 is where the game prepares the credits under normal gameplay. Let's see how we could use Intercycle Cartridge Swapping to move the program counter to address 8FE3 with the fewest number of cycles. Where is the program counter when you press the reset button? To answer this, we need to look at the 6502 assembly reset instruction. When you power on the console or press the reset button, the program counter could be literally anywhere, but the code for, say, Super Mario Bros. Is always expected to begin from address 8000. The code for tennis should always begin executing from address C1000. Battletoads starts from address FFF2, so if all of these games can start from different addresses, how does the console know where to move the program counter? Introducing the interrupt vectors. The final 6 bytes in the program ROM for a cartridge form 3 pointers. Let's focus on address FFFC and FFFD. During the reset instruction, the console will always read these 2 bytes and use them to set up the program counter. So for Super Mario Bros., which starts execution at address 8000, these 2 bytes would be 0 and 80. Here is a cycle-by-cycle breakdown of this instruction. Let's ignore the first 5 cycles because those do pretty much nothing. Cycle 6 reads from address FFFC, and Cycle 7 reads from address FFFD. If we were to use Intercycle Cartridge Swapping to beat Super Mario Bros. 3, all we would need to do is find an officially licensed NES cartridge with the value of E3 in address FFFC, then between Cycle 6 and 7, swap to a different officially licensed NES cartridge with the value of 8F in address FFFD. So, do any NES cartridges have the value we need in address FFFC? No. Are there any cartridges with the value of 8F in address FFFD? Also no. And with that, we need to make a plan B. Now, I could use a custom cartridge with a reset vector of address 8FE3 and then swap to Super Mario Bros. Between cycles 7 and 8, but I figured that solution was less interesting. If you would count that as a victory though, that would be a 7-cycle run clocking in at a final time of 3.9 microseconds. I wanted to do this entirely with officially licensed cartridges though, so let's work this out. Plan B. We either need to make a jump or branch to address 8FE3. Jump instructions take 3 cycles, while a branch that gets taken and crosses a page boundary would take 4 cycles. Despite this, the branch would technically be faster, since we could swap to Super Mario Bros. 3 1 cycle earlier. And we stop timing at the moment we make our final cart swap. Let's make a branch to address 8FE3. Address 8FE3 is pretty close to address 9000. Are there any NES games that have 00 in address FFFC? Well yeah, we already mentioned one earlier, Super Mario Bros. But are there any games with a value of 90 in address FFFD? There is a single cartridge in the entire library of officially licensed NES games. An absolute classic. Dash Galaxy and the Alien Asylum. Yeah. So, We can use Super Mario Bros. On cycle 6, and Dash Galaxy and the Alien Asylum on cycle 7. And just like that, we've moved the program counter to address 9000. To make a branch to address 8FE3, we need 2 bytes. Any branch instruction that will be taken, and then the number of bytes we wish to move the PC. I chose to use a branch on carry clear instruction, which I was able to find at address 9000 in the game Kung Fu. For the second byte, I need the value E1, which I found in a single game, Pipe Dream. And that's it! We have the entire run! With Super Mario Bros. 3 on the title screen, press the reset button and start the timer. Before the 6th CPU cycle, swap to Super Mario Bros. The value of 0 will be read from address FFFC, and the low byte of the program counter will be updated. Before the 7th CPU cycle, swap to Dash Galaxy and the Alien Asylum. The value of 90 will be read from address FFFD, and the high byte of the program counter will be updated. The program counter is now at address 9000. Before the 8th CPU cycle, swap to Kung Fu. The value of 90 will be read, a branch on carry clear instruction. Before the 9th CPU cycle, swap to Pipe Dream. A value of E1 will be read. Immediately after the 9th CPU cycle, swap to Super Mario Bros. 3 and stop the timer. From there, the program counter will be moved to address 8FE3, and Super Mario Bros. 3 will reach the victory screen. The time at our final input is 5.0 microseconds. You might be wondering, how do we test this? Oh, it's easy. All I had to do was make a NES emulator that can swap cartridges between CPU cycles. No biggie. I'm no stranger to making NES emulators. In fact, a lot of the visuals on my channel are rendered through custom emulators, but this is my most ambitious emulator yet. Not because swapping carts between cycles is ambitious, no, that took like 15 minutes to program. However, this entire project is relying on this emulator being accurate. Question 1. Why not do this on actual hardware? Let's do some quick math. On a top-loader console, the cartridge is inserted with a depth of approximately 1.6 inches. To put it bluntly, we have 175 nanoseconds to move the cartridge 1.6 inches. We need to move 2 cartridges at 520,661 miles per hour. To those who speak metric, that's about 837,923 kilometers per hour. As of this video's creation, the fastest man-made object is NASA's Parker Solar Probe, and our cartridge would need to be moving about 30% faster. This likely wouldn't be happening in a vacuum either. At this point, I wanted to know what kind of destruction would occur if we simply moved this cartridge at this speed, accounting for air resistance, so I gave the numbers to a physicist. They got back to me saying that in these conditions, the Reynolds number of this cartridge is approximately 10 trillion. That didn't really answer my question, and I don't know what that means. Question 2. How do we measure emulator accuracy? Remember, that's what we're talking about here. I made a NES emulator. In order to check if an emulator is accurate, people have made test cartridges. Some of them are pretty basic, such as just checking to see if every instruction is running as expected. The vast majority of test cartridges check for incredibly specific behavior of the Nintendo Entertainment System. Fun fact, different console revisions can have different results from the same test. Keep in mind, this emulator is specifically emulating the console that I physically own. If any test cartridge is looking for different behavior than my console, then it fails in my emulator too. Here is a list of accuracy test ROMs and how my emulator did on the tests. I got so deep into the rabbit hole of accuracy tests, I even started writing my own test cartridges. Cool. Let's also talk about the shortcomings of my emulator because I want to be honest. This emulator specifically emulates my console, an NTSC console. That means it cannot run any tests that were made for a PAL console. Additionally, I don't have every mapper chip supported, so there's actually a handful of officially licensed games that cannot be played on this emulator. Additionally, it doesn't play sound. It emulates the audio chip doing its thing, but I never got around to making it produce audio. Additionally, It doesn't have real-time controller support. It can play back tasks, it can even play back subframe tasks in real time, but it's not ideal for someone wanting to sit down and play a video game. Additionally, I'm aware of some specific PPU behavior that my emulator isn't doing. As of this moment, the PPU bus never decays because I never figured out the best way to emulate bits decaying. Additionally, my emulator does not run at a nice 60 frames a second, it runs at whatever speed your computer can run it at. In my case, that's actually faster than 60 frames a second. All of this to say, the actual computations are as accurate of an emulation of my console as I could make it. No emulator is perfect, but I'm very happy with what I made. It was built entirely from the ground up, starting with a blank .NET WinForms project. It's open source, it's fully commented, and I let the members of my Discord server vote on the name. We all agreed that Coin's Contrabulous Cart Swapulator was the best option. And they were right. Alas, I abbreviated it to Tri-CNES, or TrickNES for short, because I'm not fun. The source code to the emulator, as well as my own test ROMs, can be found on my GitHub, link in the description. Now that we have the emulator, let's make the TAS. I'd like to open this section of the video by saying that all the good 3-character combinations for file extensions have been used elsewhere. Since this is my own emulator, running my own TAS files, I got to create my own file format. For a standard non-cart swapping TAS, you can import a TAS file from a series of existing formats. For a cart swapping TAS, you'll need a .3ct file. Here's the gist of it. The first line is how many cartridges are being used. The following n lines are a list of the cartridges used. This is used to create an array of cartridges. Then, the rest of the lines until the end of the file are in the following format. Just before this cycle, swap to the cartridge at this index of the cartridge array. I'm going to be using Super Mario Bros., Dash Galaxy and the Alien Asylum, Kung Fu, Pipe Dream, and Super Mario Bros. 3. Set these up to swap in on the correct cycles, and there we go. That's the .3ct TAS file for this run. Running the TAS. In the toolbar for my emulator, I have a drop-down labeled TAS, Load .3ct TAS. Select the TAS you wish to watch. There are some settings for clock phases, but don't worry about them, see the footnote if you're interested. We're going to be running this TAS from pressing the Reset button, so I'll check From Reset. By clicking this Load Cartridges button, we make sure we actually have all the cartridges this TAS requires, and this sets up the array of cartridges. Now I'll click Run TAS. Alright! Now at this point, I hope you're very curious about the run that starts from pressing the Power button, because it's about time we talk about it. Okay, so this run is starting from pressing the Power button, assuming the console has been at rest. First of all, what would happen if we ran the previous TAS from the Power button? Just like before, we're going to run a branch on address 9000 to address 8FE3, but when we insert Super Mario Bros. 3, hey, this isn't the code we want to execute. We have the correct cartridge inserted, but the function to load Mario 3's credits is actually over here in address CFE3. What? Let's talk about mapper chips for a moment. A 40 kilobyte game like Super Mario Bros. Has 32 kilobytes of program ROM and 8 kilobytes of character ROM. Conveniently, the NES has 32 kilobytes of address space dedicated to the program ROM and 8 kilobytes of VRAM dedicated to the characters. So when NES games began getting larger and larger, they needed a way to load even more of the ROM into the same amount of space. Take Super Mario Bros. 3. This game has 262 kilobytes of program ROM. So if the game's program ROM is 8 times larger than the space dedicated to where the ROM is accessed, how does the game work? Introducing ROM banks. This cartridge uses the MMC3 Mapper chip, which works something like this. Split the program ROM into 8 kilobyte banks. The last program bank in the ROM will always be accessible from address E1000 through address FFFF. The second to last program bank will also always be accessible, but it could be loaded at address 8000 or at address C1000. Then, you get to choose which banks get loaded in the other locations by writing to some registers. The process looks like this. Write to address 8000 to set up the bank swap mode. Write to address 8001 with the value of the bank you want to swap in. Wait a second, we're writing to address 8000? Isn't address 8000 dedicated to the read-only memory? Yes. And since writing to ROM does nothing, mapper chips will frequently use writes to this range for their registers. So if we want to put, say, program bank 5 in the address A1000 to BFFF range, we could start by writing 07 to address 8000 to set up the bank swap mode for this location, then write 05 to address 8001 to perform the bank swap. Real quick, let's take a look at bit 6 of the bank swap mode. Since the second to last program bank is always loaded, this bit will determine the location of it. If this bit is set, this bank will be loaded from address 8000 to 9FFF. If this bit is cleared, this bank will be loaded from address C1000 to DFFF. Quick recap since mapper chips are a doozy. The NES uses address 8000 through FFFF for reading from the game cartridge, but this cartridge has so much data that it cannot fit entirely in that region. The game is broken into program banks, some of which are always loaded. In Mario 3, the code that loads the victory screen is always loaded, but this code could be loaded in one of two locations, and in the case of our TAS, it's the wrong one. In order to correct this, we need to make some changes to the code we're running in our TAS. We'll start by loading the A register with the value 40, then storing A in address 8000. This will make sure that the code we want to execute is in the right place. Now we branch to address 8FE3. Alright, problem solved. Let's run the new TAS. That didn't work. What went wrong this time? During the IRQ routine, see the footnote, Mario 3 will check if address 7964 has the value 5A. Otherwise, the game reboots. To be honest, I'm not sure why this line of code exists. The game writes the correct value to this address during the code it runs when the game boots, but why do any of this? Plus, now I have to explain why there's even RAM here. Usually, the NES only has RAM from address 0 to address 7FF. This RAM gets mirrored through address 1FFF. But the MMC3 Mapper chip has external program RAM that's stored on the cartridge instead of the console. The console can read this RAM from address 6000 through 7FFF, but only if the MMC3 chip has this external RAM enabled. Okay, so for our run we need to enable this external RAM by writing to address A1001, and we also need to write 5A to address 7964. The value written to address A1001 just needs bit 7 enabled, so we'll write a value of 80. Then, we'll write 5A to address 7964. Since a value of 5A has bit 6 enabled, let's reuse this value for our write to address 8000 and save ourselves from running two load instructions. Quick recap, Mario 3 has some magic number stored in some magic address, and if the expected value isn't there, the game reboots. This also happens to be inside the MMC3 chip's external RAM, so we need to enable that RAM and then write there. Now our code looks like this. Load the value of 80 into the A register and store it in address A1001. Load a value of 5A into the A register and store this value in address 8000 and 7964 before finally jumping or branching to address 8FE3. Alright, problem solved again. Let's run the task now. Okay, forgive the jargon, but this section's getting pretty long. The audio chip is creating IRQs, and we need to tell it not to do that. We're gonna write 5A to address 4017 as well to prevent them. And finally, the task will reach the victory cutscene. So, final recap. We want to run this code. This code, when assembled into bytes, looks like this. Now, we need to find this string of bytes using Intercycle Cartridge Swapping. Oh man, this is a lot of specific values, and there's a lot of games to check. Let's automate this process. This is a blank Visual Studio C#.NET WinForms project. I've added a button and a text box, and what we want is to push this button and have this text box get filled in with a list of cartridges and a starting address that we'll use for this task. Basically, I want this program to figure all this out for me, so I have to do as little as possible. Let's figure this out. To begin with, here's every officially licensed NES game in a folder. Don't worry about it, here's photo proof that I physically own all of them and also every revision. Since games like Mario 3 use mapper chips and have non-deterministic power-on states, I created a .bin file for each NES game that only contains the bytes that are guaranteed to exist from the moment the console is powered on. With every NES cartridge formatted this way, we can overlay every single cartridge from address 8000 through address FFFF. I wanted to visualize this, so here's a fun graphic. It's a remarkably large image, and I bet YouTube compression is destroying it, so here's just a few addresses of it. The x-axis is the address, and the y-axis is the value of the bytes in each cartridge at that address. I've colored a pixel white if that value can be found at that address. For instance, there is at least one cartridge with the value of hex 18 at address 8002. Cool. And while we're looking at this image, I just wanted to point out how cool it is that you can see patterns. There's a lot of really cool curves as well. Here are the interrupt vectors in case you're nerding out about this image as much as I am. As you scroll the entire image, you can kind of see this line gradually going from a value of hex 80 to hex FF, which is definitely a bunch of instructions reading from nearby lookup tables or jumping to nearby functions, and I absolutely love how you can see that in this image. But I am getting a bit distracted, so let's get back on track. With this complete list of addresses and values, we simply need to find if the pattern created by our desired code can be found in this set. I wrote a function called determine if a specific string of bytes appears anywhere in the entire library if you allow cart swapping between bytes. This function will start at address 8000 and loop over the entire address space. Since we know we can't move the PC to every address using the reset instruction, for instance, we couldn't move it to address 8FE3, I only check the addresses that we could begin executing from. This is checked using a lookup table of booleans, which I set up in a function I wrote called determine where all carts can move the program counter during the reset operation if you're swapping carts between cycles if you have access to the entire officially licensed library of Nintendo Entertainment System cartridges. Now we need to find the 19-byte string that creates the assembly code we want to run in order to win Mario 3 from pressing the power button. Here's our desired byte code in an array. If index I of our byte code can be found at address j, increment I and check the next index and address. This repeats until it either finds the entire byte code or it fails to find a byte, in which case increment the address j and try again. Once a match is found, we simply take the value j as the starting address and find which cartridge has the value byte code I at address j. Print its name, and then repeat for the entire byte code. And just like that, we have a winner. To be honest, this set of cartridges wasn't the most exciting. Sure, it'll work, but I haven't even heard of most of these. I thought it would be fun to add weights and pick the list of cartridges that has the most popular, well-known results. This was done using a function I wrote called objectively rank every officially— okay, you get the joke. I also wrote a few hundred alternate strings of bytes by using different registers or shuffling the order of instructions around. That way we might find a better list of cartridges that our original byte code wouldn't encounter. Here was the best I could find. And honestly, what a list. I've got a real treat for Xanac fans, if any, because you get to be included too. With the exception of Xanac and Breakthrough, these are all cartridges that I'm very familiar with, which makes me much happier than that first list of games I generated. I made the .3CT task, ran it in the emulator, and it works out just fine. Let's take a look at every cycle of this run and see what's going on. Notably, Luigi wins this run. But why? At the moment the console is powered on, the contents of RAM are in some resting state. To be more specific, when the console is powered off, the bytes in RAM decay in a specific pattern. This resting pattern can be different depending on the console revision and probably the manufacturer of the RAM chips, but for my console, it has this pattern. Since address 726 determines what player we are currently playing as, 0 for Mario and anything else for Luigi, the resting value of FF means Luigi wins. And now we move on to run 3. Super Mario Bros. In Super Mario Bros. 3, we simply needed to move the program counter to a magic location and the victory screen is prepared for us. It's not quite so easy for this game, as the victory screen requires the game to be in World 8 Level 4 and for Mario to land on the axe. In other words, we need to figure out how the game defines in World 8 Level 4 and Mario about to land on the axe as values in RAM. If you saw my task where I play the Bad Apple music video inside Super Mario Bros., you may recall that it ends by placing Mario directly above the axe in 8-4. So how did I achieve this effect in that task? Well, I overwrote every value in RAM. It's almost like loading a save state. If the contents of RAM are set up in the exact same way as they would be when a normal run of the game reaches this point, then it's indistinguishable from a normal run of the game. Now here comes the optimization problem. Replacing the entire contents of RAM would require modifying about 2,000 bytes. But who said we need to replace the entire contents? Let's find the minimum number of bytes we would need to modify in order to beat Super Mario Bros. My console has this resting pattern for RAM when powered on. I found 85 bytes where if any of these are in the resting state, the game will not be completed or there might be some visual bugs which I wanted to avoid. Like before, here's the list of load and store instructions. This will set up all 85 bytes, and then I'll also enable the non-maskable interrupt and jump to address 8057. Now, this entire thing converted into bytes is outrageous, and unfortunately I had no results when I ran the C# code from before with this byte code. You might recall how in the Mario 3 task, I shuffled instructions around in order to try more byte strings. I actually created 576 permutations of those 4 steps. How many ways could our Mario 1 code be reordered? It's apparently this number. 3.8 duotrigentillion. I think it goes without saying, but I'm not going to be able to check every permutation to see if I can find a working set of cartridges. I'll just assume the answer is no. Perhaps we're thinking about this a bit too one-dimensionally. If we're able to start a load instruction and then swap to any other cartridge, why not take full advantage of that? What if we find the value for the load instruction, followed by a single address that could contain all the values we need by choosing different cartridges? To make this run work, I found a few locations that works for all of the LDA and STA instructions I need, and I can run jump instructions between them. So instead of this entire string of bytes being sequential, I'll be jumping back and forth to an address with a load instruction that can get me all the values I need, to an address with a store instruction that can write to wherever I need. Now we're looking at 250 instructions, but I was able to get a list of cartridges for this to work. I made the .3ct file, and let's check it out. Okay, cool, so that looks wrong. I mean, we visibly won the game, technically. The color palettes are all wrong, there's a ton of garbage on screen. What is happening? Well, I'm glad I asked. Just like the CPU RAM, the picture processing unit's VRAM has its very own resting state. The garbage background tiles and attributes are just using this pattern. What about the color palettes? It was briefly mentioned in the footnote back when I first introduced my emulator, but the palette RAM of every console has a unique pattern that you'll find when powered on. The pattern for my console looks like this. So, we might have set up the CPU RAM for the victory, but we've completely neglected the VRAM, which results in this incredible mess. What kind of steps would we need to take in order to fix the background and color palettes? The CPU of the console is not directly connected to the picture processing unit's VRAM. Which begs the question, how could our code modify the VRAM? This is where the PPU registers come in. Essentially, there are dedicated addresses that the CPU can access in order to interact with the picture processing unit. Let's say we want to write to VRAM address 400. Unlike writing to the CPU address space, where we could just say STA400, writing to the PPU address space requires a few more steps. The PPU has a register called V, which is essentially the read-write address of the PPU. If you want to read from or write to anywhere on the PPU address space, you need to first set up this read-write address. This is done by performing 2 writes to the CPU address 2006. The first write will be the high byte of the read-write address, and the second write will be the low byte of the read-write address. If we want to write to PPU address 400, we could begin by running LDA4 STA2006, LDA0 STA2006. With the PPU's read-write address pointing to PPU address 400, the CPU can now interact with that address through CPU address 2007. Let's just write the value 0 to this PPU address. This is done by running STA2007. It's also worth noting that whenever the CPU reads or writes to CPU address 2007, the PPU's read-write address is automatically incremented. This makes reading or writing multiple consecutive PPU addresses really convenient, as you don't need to keep writing to address 2006 to set up the next PPU address. With all of that information, let's go back to our task and fix the color palettes. Oops, here I go making you juggle multiple pieces of information before continuing. The picture processing unit needs to warm up after booting the console. It intentionally rejects any input for approximately 30,000 CPU cycles. So we need to wait for about 30,000 CPU cycles. This time can be spent making the initial changes to RAM that this task needs, but that only takes about 800 cycles. We genuinely just have to wait. Okay, now let's fix the color palettes. The palette RAM is accessible when the high byte of the read-write address is 3F. To correct the color palettes, we begin with LDA3F, STA2006, LDA0, STA2006. Now the read-write address is at address 3F00. Here are the colors that we want to use. We can set these up by repeatedly running LDA for the next color and STA2007. With the color palettes all set up, let's fix the background. Just like before, we need to set up the read-write address to a new location. This time we'll move it to address 2000, which is where the background name table is. We'll need to overwrite 2 kilobytes. Here are the values we want. Turning this into a nice optimal string of assembly code is pretty easy, but we've already learned in the previous run that our nice optimal code can't always be found. With how this code contains hundreds of STA 2007 in a row, I wanted the final code to be a bit more optimal than just putting a jump between every one of these. For instance, I would be able to create 2,762 copies of STA 2007 in a row, starting at address DED1. I don't need to put jump instructions between these. My idea was to pretty much make a really large sequential string of bytes, but procedurally, instead of forcing the most optimal string to work. Run all the STAs you need, and then if you need to change the value of the A register, instead of jumping to some known location, I can just run as many no-op instructions as it takes until I can create an LDA instruction that I need. In many cases, I don't even need any no-ops at all, and it just happens to be optimal anyway. So to recap, this might not be the most optimal, we're just going for something that works here. And since there's thousands of steps, we're going to create the entire thing procedurally. Now to make the C# code to do all this for me. So now, in this order, we update everything in RAM, spin for about 30,000 CPU cycles, jump to code that updates the color palettes, and jump to code that updates the entire background before enabling the non-maskable interrupt and jumping to Mario 1's spinning loop. And finally, we convert that into a .3ct task. Here's the .3ct file that I generated with it, and yeah, it works. Power on the console, and after about 9,500 cartridge swaps, we've beaten Super Mario Bros. In less than 2 frames. It's also visually identical to any other completion of the game. Oh yeah! Where do we go from here? With this proof of concept, I have demonstrated that running arbitrary code through cart swapping is technically possible. I still haven't tried this on hardware, though I imagine you might be able to put something together with a bunch of 72-pin connectors and a really big multiplexer. Just so we're clear, if it does work on actual hardware, Intercycle Cart Swapping could be used to set up the state of RAM or VRAM with any values you want in any address you want. Move the program counter wherever you want and then insert any cartridge of your choosing, entirely with official cartridges. Total control arbitrary code execution for every single NES game. Do with this information what you please. At this point, I think this is just begging the question, can we beat Mario 3 even faster? I honestly don't know. I'm gonna say probably not, but I will happily be proven wrong. There's a handful of stuff that I wanted to talk about in this video but never got around to explaining, such as the CIC chip, which can cause problems if this isn't performed on a top-loader console. Check out the footnote. And finally, let's address the elephant in the room. This is stupid. This is the most convoluted way I could imagine to execute code on a console. It requires tremendous work to determine exactly what code you want to execute, what address to execute it at, and which cartridges can be used to execute it, and that's assuming it can be executed at all. It is a method that is so far beyond the realm of human viability that it would require moving cartridges at multiple hundreds of thousands of miles an hour, breaking the record for the fastest man-made object. And the end result of which is a speedrun that's so fast the run ends before anything can even be drawn on screen. All the moving parts are done moving before the human eye can even process it, which leads to a run with little to no intrinsic entertainment value. At this point, one has every right to ask, why do this? Why go to such lengths for a run that many would say isn't entertaining to watch? Well, because I do think the method behind how this run works is entertaining. I think this was an interesting optimization problem, and I'm not sure if anybody out there would have taken this as seriously as myself. But I also made this run because of one more undeniable fact. On this channel, I don't do things because they are easy. I do things because it's a great excuse to make another NES emulator. Thank you so much for watching. This video had about 10 seconds of video game footage for the whole thing, and I've probably been driven into madness during the editing process. This video was way more work than I thought it would be, so I'm probably going to make some shorter videos that don't take multiple months to make. On top of videos surrounding the NES, I've also been wanting to branch out a bit and make videos covering some game development stuff. I've been wanting to make another game, and I think some devlogs would be fun to put together. I know that's not at all the kind of content I've made on my channel up to this point, but I'd like to give it a shot. On the topic of games that I've made, Fantastic Fist is on sale for 80% off for the Steam Spring Sale. My videos are supposed to serve as documentation, so I'm not very motivated to put a sponsorship in the middle of it. I hope you don't mind me advertising my game here at the end though. Anyway, if I failed to explain anything in this video, I will happily answer your questions in the comments. Your feedback matters. And hey, if you liked the video, don't forget to star my GitHub! Yeah! Woohoo! That was an organic call to action, right? That felt good. And with that, this video is done. I will see you around. By the way, task videos, I plan to try and submit this for April Fool's Day this year. You have been warned.